In this video, we are going to discuss Resistor Transistor Logic RTL circuit to design NOT gate, NOR gate, OR gate, NAND gate and AND gate. At the end, I will discuss one problem and also I will be giving you one easy homework problem. First, we'll start with NOT gate. The Resistor Transistor Logic, the name suggests that it contains two elements. One is transistor, that is the main element, and along with the transistor, this one will have few resistors to bias this circuit, okay, and voltage sources will be there to design the NOT gate or any other gate. So we'll discuss this thing in detail. Let us understand what is the NOT gate. This is a symbol for NOT gate. So be careful here. This kind of shape is sometimes also used for amplifier. But this bubble is the most important thing. Because of that, it is a symbol for NOT gate. It is also called inverter. So if I apply X as an input to this inverter or NOT gate, the corresponding output Y, the relation is given by this truth table. X can take two logic levels, either it is 0 or 1. 0 means the low voltage is corresponding to logic 0, and if input voltage is high, then we'll call it logic high. So if input voltage is low, means logic 0, then corresponding output is 1, Y is 1, and when X is 1, output is 0, it is just inverted. So 0 is becoming 1, 1 is becoming 0, that's how it is called inverter, or it is a complement. Y is a complement of X, it's a NOT gate. We can write Y as complement of X, X bar, to denote it's a complement of X. So whenever you apply 0, you are going to get opposite one, that is 1, and if I apply 1, you will get 0. Now how to design this NOT gate using transistor resistor logic. So this is basic transistors. It is having 3 terminal, base, collector and emitter. I have considered here NPN transistors, okay. P to N, there is one arrow, this is the emitter side. Now this design is very simple. So first we'll consider emitter to ground, and from this collector we'll connect to source VCC through resistance RC. Now in the base we'll add the input, but we will put one resistance as well, the RB, to limit the current at the base side. So this is the exact input X, and we will collect the output from this collector end, that is your Y. Okay, this is your input X, this is output Y. Now we need to understand how it will work. Now here RC and RB, these two are required so that the transistor is biased properly. It is having 4 operating regions that you know. And out of these 4 operating regions, in digital logic design, we will be using only 2 regions. One is cutoff, other one is saturation. And those other 2, that is forward active and reverse active regions, those are used for amplifiers, not for designing gate. Okay, remember this thing, that transistor should be either cutoff or saturation region to design the logic gates. Now what is a cutoff? Cutoff means there is no current through the device. The IV is 0, base current is 0, collector current is 0, even I is also 0, all are 0. So this situation is called switch off. Nothing is there, no current is flowing anywhere. So this is completely switch off. It is an off open circuit. Okay. And on the other hand, saturation means huge current. Okay. So IB is here large, IC is also large, but what is happening, this one, the collector emitter potential is becoming 0, almost shorted. It is almost shorted to ground. This is called switch on. Okay, we can consider it switch off, and this is a switch on. Okay, switch on means shorted, switch off means open circuit. So what I can say in short? So this cutoff means open circuit. This will behave as open circuit. In saturation, if it is in saturation transistor, it is collector emitter is short circuited. Okay, now how to make this thing cutoff or saturation region? Based on these two junctions. One is base emitter junction. This is the base, this is the emitter. Between these two there is a junction, and this base and collector is another junction. If both the junctions are reverse biased, then it is cutoff region. Okay, reverse bias, you know that this diode, this could be considered as a diode, this P2N diode. If this diode is reverse biased, no current is flowing. Base collector is also reverse biased, no current will flow. So every current, IB, IC, everything will become 0. Okay, but for saturation region, it is just opposite. Both the junctions are forward biased. So this is forward biased, then you can expect the current IB, but we should choose RB in such a way that we will get sufficient current, huge current to this one. Okay, and RB should be chosen in such a way that this junction, base collector junction, is forward biased again. Okay, if it is forward biased, then only it will be under saturation region, and collector emitter is almost shorted. Actually, the VCE will be around 0.2 volt, that is near about 0 volt roughly we will consider. So this is switch on, it's short circuit, that we will consider. So I have discussed this cutoff, saturation, forward active, reverse active in detailed in my previous videos. You can follow that one. I will be giving you the link at the below. Now we will try to understand these things. When the input is 0, you can see if input X is 0, if it is 0, then this junction is reverse biased. Because base emitter potential, if it is more than 0.7 volt, then only this junction will be forward biased. So if X is less than 0.7 volt, means low signal, a capital X equal to 0 means low voltage. I want to mean that it is less than 0.7 volt. So if capital X is less than 0.7 volt, this base emitter junction is reverse biased. And this VCC is generally high, about 5 volt. Okay, so this is high, the collector is positive high, and base point is 0.7 only. So this junction will be reverse bias, because this is NPN transistor. This is N side, this is P side, this is again N side. So this junction is forward biased, this is reverse biased. When X, so this is, if I make it more than 0.7 volt. Okay, but in digital logic design, what we are doing, we will consider a capital X equals to 0 or 1, but we will choose RC and RB in such a way that this base collector is, when it is reverse biased, this is also reverse biased, means cutoff, and when this base emitter is forward biased, this is also forward biased, it is means saturation. Okay, now when X equals to 0, this is not forward biased. Okay, if it is more than 0.7, then only it is forward biased. Okay, so 0 volt, if I apply logical 0, then this is reverse biased, automatically this is also reverse biased. It is in cutoff, no current is flowing, so I can assume that this transistor is not working, it is behaving as open circuit, so it's switch off. So if it is switch off, it is disconnected from the ground, it is now connected to VCC, we can expect high potential here. There is no voltage drop almost, okay, because current is not flowing, no drop across RC, so almost same potential we will get here VCC. That is logically high. Okay, so if I apply 0 volt here, we are going to get logic high here. So 0 input, output is 1. because transistor is open circuit. Now, if I consider high potential at the input, what will happen? Transistor will be on the saturation region. So we need to choose RC and RB to power way. Then only both the junctions will be forward biased. And if it is forward biased, it is shorted. This collector emitter end is shorted. It is shorted to ground. So this potential will become 0. So huge current will flow. IC will be there. And voltage drop will be IC into RC. So you are going to get 0 potential here because it is connected to ground now. So when you will apply 1, you are going to get 0 output, logical 0. Thus it is input 1 and output 0. You can see this is inverted. Input is 0, output is 1. When input is 1, output is 0. This is very simple circuit. So this is a simple circuit you should remember. Okay. Now we are going to design NOR gate. So what is the meaning of NOR gate? So negated OR. A or B. If A or B is 1, is high, then output is 0. That is called NOR gate. If any of these two A or B, they are logically high. Just see this, what I am saying. If A or B, any of these two is logically 1, then output is going to be 0. That is called NOR gate. Okay. So here you can see this 1, 1. So obviously both are 1. We are going to get 0. Next one, it is a 1, 0. This A is 1 and B is 0. Then also we should get 0. And this is also we should get 0. Only when both A and B are 0, 0, then it will become 1. So it is opposite of OR gate. In OR gate, if any of these two input is logically 1, output is 1. This is the OR. Okay. And NOR is just opposite. If any of these two or both of these two are 1, then output is 0. Right. So this is very important things. Now, how to design this kind of NOR gate? So very simple circuit. Earlier we had only 1 transistors. Now if I have 2 input, I need 2 transistors, but these 2 transistors should be connected in parallel, and then from VCC to these transistors, this circuit is RC is connected. Okay, and we will be taking output from this end. This is your output end. This is the exact input A. This is the input B. Now we want to understand how it will work. It is very simple, very similar operation. So you understand that when transistor is on, it is saturation region. It is shorted to ground. When transistor is off, it is open circuit. It is connected to this side. Okay, same philosophy we will be using. So first we will consider both are 0, 0. If this is 0, this is 0. As I said that if input is 0, transistor is off. It switch off. So both the transistors will be switch off. Then what will happen? If this is off, open circuit, this is off, open circuit. See, no one is connected to ground. So eventually it is connected to VCC. So you are going to get high output, logical 1. So if both are 0, 0, then output is high because it is connected to VCC. It is not connected to ground. So it is connected to VCC. No drop is there. Almost full voltage you will get here. But if you see, if it is 0, 1, this is 0, this is 1. A is 0 means this transistor is off, open circuit. And B is 1 means this transistor is on, it's short circuit. So what will happen? This side is open, fine. But this is shorted. Because of this path, the output is shorted to 0. If any of these two is shorted, any one is shorted, it is fine. Output will become 0. So right now 0, 1 will make the output 0. Okay. Similarly, if it is 1, 0, this time this is shorted, this is open, but because of this path, it is connected to ground, output is again 0. Again, if both are 1 1, both are sorted, it's fine. Obviously it is grounded, so output is 0. Okay, so you can see that when transistors are connected parallelly, then if any one path is sorted to ground, output is 0. Meaning is, so it will be sorted if and only if that input is logically high. That's how, if any one of the input is logically high, that corresponding switch is sorted to ground and output will become 0. Very simple logic. Okay, we can extend this idea for more than 2 input. Okay, so here this for NOT gate we write in this way: A plus B, A or B, and then inverted. So it is a NOT gate, not of A or B. Okay, negated A or B. So we can extend the idea for multi inputs, more than 2 inputs, A, B, C, suppose all are connected parallelly. So obviously we'll get if any one of this input is 1, output is 0. Okay, if all are zeros, then only output is 1, otherwise every time it is 0. So it is written as y equal to A or B or C, then 1 bar, complement of that. Okay, so how to make then OR gate? We'll consider this OR gate. So you can understand that NOT gate we have designed. OR gate will be just opposite of this one. Means any one of these two is 1, then output is high. You can see 0 1 will give you 1, 1 0 also give you 1, because this is 1, and here both are 1, it is also 1. So it will be 0, output is 0 if all the inputs are zeros. Okay. So how to design? So we have already seen that if this is the circuit for NOT gate, here you will get NOT output. So if I invert it further, we will get OR. So I need to include one inverter here, one NOT gate here. So I'll introduce one NOT gate. So one simple resistance, and this is one transistors, and we'll take output from this collector, we'll get inverted of this one. So this part is your NOT gate, followed by a NOT gate, we'll get OR gate. That's simple logic. Okay, this is the easy way to design OR gate. Now, so if I consider 2 transistors in series instead of parallel combination, then what we will get? Okay, now they are cascaded one after another. So if both are on, okay, if both are on, then only it is connected to ground. If any one is off, it is not connected to ground. Okay, so if both are 1 1, then only it will be connected to ground and output will be 0. Is it right? Okay, if any one is 0, that corresponding transistor is off and it will be connected to VCC. So we'll study this thing first. If it is 0 0, both are 0 0, both transistors are off. Okay, so this is open circuit, this is open circuit. So this output is directly connected to VCC, so it is 1, logically 1. Now if it is 0 1, it is 0, this is 1. So 1 means it is sorted, fine, but because of this A is 0, it is open circuit. If this is open, there is no current flow here. It is not connected to ground. No current can flow because 1 is off. Okay, so output is connected here to VCC. It's not connected to ground. So again, we will get output 1. Similarly, if it is 1 0, A is 1, B is 0. A 1 means it is closed, but this is open, but again same result, because no current flow, it is just connected to VCC, output is high. But if both are 1 1, then both transistors are closed, so this is circuit path, closed path, a huge current will flow, and here this power potential will become 0 because it is sorted to ground. No voltage drop here, it is sorted. Here huge voltage drop, full voltage VCC will be drop across the RC, and you will get output 0. So this is the truth table. 0 0 is 1, 0 1 is also 1, 1 0 is also 1, but 1 1 is 0. If both A and B are 1, then output is 0. It is the negative of AND gate. The AND gate says that if both are 1 1, output is also 1. That is called AND. A and B, okay, both are 1 1, then only output is 1. But it is the opposite of AND gate. Thus it is called NAND. It's a NAND gate. Okay. So the symbol is this one. This is the symbol. Don't forget to put this vowel. This indicates the opposite of AND gate. If I remove this vowel, it will become AND. Okay. We write A and V. At the end, we'll put the complement. Okay. This bar. So what is the AND gate? How to design? So from this NAND gate, if I introduce one NOT gate followed by this one, we'll get AND gate. That's simple. Already we have discussed these things. Whenever the transistors will be in series, we'll get NAND first. We'll get the complement bar here. Okay. Then to remove this bar, we need to put another NOT gate. So negative of this one, this bar is removed, we'll get only AB. Okay, right. Now I'll give you one simple problem, but very interesting. Can you find the expression for this Y in terms of A, B, C, D? Is it difficult? It's not difficult at all. So how to analyze this one? So you need to understand how transistors are connected, whether series or parallel. Okay, and again I said that the output is always something bar we are getting, no? Because if it is sorted to ground, output is 0. So we need to understand when it will be sorted to ground, right? So that so this path could be sorted when? This path will be sorted if both A and B, they are on. Okay, so this path, if I consider first A and B, because they are in series. So this is one path, A and V, AV we'll call it. Now with this is one branch, parallel path. So AV is one path, another path is C, they are in parallel. So I can write AV plus C, AV or C. So this is one stage. Okay. So this path, AB or C, if anything is sorted, then we would consider that D is connected in series with this one. This is one block, this is one block. With this block, D is connected in series. So with this block AB plus C, D is now connected in series, so it's an AND operation. So with this, D is multiplied. It is D. So at the end, we need to take the bar, because if all are sorted, if this path is sorted somehow, either through this path or through this path, it is sorted, then output is going to 0. So we need to put a bar here, we'll get Y. That's simple. So Y will be the bar of AB plus C with the bracket and D. So you need to identify the transistors, how they are connected, the blocks. Here this is the two parallel paths, that's how these two. This path is AB and this is C, AB or C, and with this D is series, this is the AND. At the end you should put the bar. Okay. Now I'll give you one homework problem. If this video is useful, you can press the like button, and if you want to get this kind of videos, you may subscribe this channel. Now, this is our homework problem. Okay, can you find the expression for this Y? Look at the problem carefully. Try to understand these things, how I have discussed. All the blocks, consider this block, this stage, consider this one, this stage, and this one. Okay, then try to find out the Y. Okay, so one hints that what is the value here, expression here, and that could be the input for this stage, and for this transistor this is the direct inputs are given. Okay, so I hope you can find out the expression for this y, and if you get the result, please share your result in the comment sections. I will discuss with you. Okay, thanks for watching. We'll discuss more problem in my future videos. Thank you.